Hello, in this video under the module 1 of VTU syllabus, I am going to explain equivalent force constant for springs connected in series and equivalent force constant for the springs connected in parallel, and also I am going to explain free oscillations. First, I am going to take up equivalent force constant when springs connected in series. Next, so here is a picture. So by making use of this picture, we can able to explain the expression for spring constant when the springs are connected in series. So consider a load which is suspended through two springs S1 and S2 with the spring constants K1 and K2 in series combination. Both the springs experience same stretching force. Let delta x1 and delta x2 be their elongation. Next, here the total elongation is given by delta x is equal to delta x1 plus delta x2, which is equal to F by K1 plus F by K2, where F is force acting on the body downwards. So the above equation can be rewritten as F by K equivalent is equal to F by K1 plus F by K2. So further, here F cancels throughout. So the above equation can be written as 1 by K equivalent is equal to 1 by K1 plus 1 by K2. So this is the expression for force constant when series combination. Next, I am going to explain the expression for spring constant for springs connected in parallel. So in this picture, we can look at springs connected in parallel. Let K1 and K2 be the force constant for the two springs. Now consider a load suspended through springs with the spring constants K1 and K2 in parallel combination. The two individual springs elongated by x but experiences the load non-uniformly. So the two springs experiences the extension x. Next, the total load across the two springs is given by F is equal to F1 plus F2, or K equivalent into delta x is equal to K1 into delta x plus K2 into delta x. So the K equivalent can be written as K1 plus K2. That means K equivalent is equal to K1 plus K2. So this is the expression for force constant for springs connected in parallel. Next, I am going to explain free oscillations. The oscillations are said to be free oscillations when there are no external forces acting upon it, by the time the object oscillates with natural frequency. So we can take electrical oscillations into account for explaining free oscillations. So let us consider a capacitor and an inductor connected in an electrical circuit as shown in this picture. Next, if the capacitor is initially charged and when the circuit is closed, we find that the charge on the capacitor oscillates. The voltage across capacitor is equal to Q by C here, and the voltage across inductor is equal to L into d square Q by dt square. And here L is the inductance value and C is the capacitance of the capacitor. For the above equation, we can write Q by C plus L into d square Q by dt square is equal to 0. Further, on simplification, we will get d square Q by dt square plus Q by LC is equal to 0. By comparing this equation with the another equation, that is d square x by dt square plus omega square x is equal to 0, the solution can be written as Q is equal to A cos omega t plus B sin omega t. So the equation can be written as Q is equal to A cos omega t plus B sin omega t. Here the angular frequency omega is equal to 1 by square root of LC. Next, in this picture we can look at a table. So here I am going to explain similarities between mechanical oscillations and electrical oscillations. So here in the table we come across variable, mechanical property and electrical property. If we consider independent variable, the time comes under mechanical property. Similarly, time is comes under electrical property. If we consider dependent variable, the position x comes under mechanical property and charge q comes under electrical property. And inertia, if we consider, mass comes under mechanical property, whereas inductance comes under electrical property. And resistance, if you consider as a variable, drag coefficient which comes under mechanical property, whereas resistance will comes under electrical property. And stiffness, if you consider as a variable, the force constant K comes under mechanical property and 1 by C comes under electrical property. And resonance frequency, if you consider, omega naught is equal to square root of K by M under mechanical property, and omega naught is equal to 1 by square root of LC under electrical property. And if you consider variable as energy, under mechanical property, potential energy is equal to half kx square and kinetic energy is equal to half mv square. Under electrical property, the corresponding values are half cv square and half li square. So these were all the data we can look at when we consider mechanical oscillations and electrical oscillations into account. Thank you.